Hi, my name is Jiang, and I will be presenting our work, HandAvatar, Embodying Non-Humanoid Virtual Avatars Through Hands. This work is done in collaboration with Zhipeng, Mufei, David Lindlbauer, and Yukang. Past researchers have shown that in a virtual reality environment, users can gain a strong sense of embodiment when they use their body to control a humanoid avatar. This highly embodied and immersive experience is enabled by the user and the avatar's identical body structures, which also makes the mapping between the human and the avatar intuitive. On the other hand, the evolving VR technologies also show great potential in controlling and embodying non-humanoid avatars in applications like animation and gaming. This can potentially enable a new immersive human as non-humanoid experience that's improbable in reality. Yet, the biggest challenge is how to map human body parts to a topologically different non-humanoid avatar. To answer this question, we propose HandAvatar, which enables users to control and embody non-humanoid avatars with their hands. HandAvatar leverages the high dexterity and coordination of users' hands for flexible control. We contribute a novel optimization-based approach for mapping users' hands to arbitrary non-humanoid virtual avatars. The mapping optimized by HandAvatar is defined by a joint-to-joint mapping and the reference pose pairs. The joint mappings map each control joint on the avatar to one hand joint such that the control joint mirrors the hand joint's movement by sharing its local joint rotation. The reference pair of avatar and hand poses specify the hand pose used to control the avatar and are used in combination with the joint-to-joint mapping to infer current avatar poses. With the optimized joint pairings and the reference pose pair, we can calculate the corresponding avatar pose given the current hand pose, which enables us to control the non-humanoid avatar in real time. We started with a two-phase observation study to understand how users design their own hand-to-avatar mappings and what are participants' criteria for good mappings. 8 non-humanoid avatars that cover different habitats, topological structures, and motion methods were chosen for this study. We invited 12 participants to design hand-to-avatar mappings by first posing according to the reference avatar pose, then selecting the avatar control joints to hand joint pairings. In the vote phase, we re-invited 8 out of 12 participants to view 6 of the 12 mappings designs, which include their own designs, then vote out the top 3 ones. Based on the mapping designs and the interviews, we summarized the taxonomy of user-design mappings. The breakdown shows that users tend to design form-driven, balanced, and left-right symmetric mappings that give them full control over the avatars. In the vote phase, the participants did not always prefer their own mapping designs. They also have consistent preferences as each tested avatar only had 1 or 2 top-voted designs. The interviews also revealed that the participants prioritized control, intuition or structural similarity, and comfort when voting for the designs. We therefore optimized these criteria in our mapping generation algorithm. To reiterate, the goal of the algorithm is to find 1. The hand joint to avatar joint mappings, and 2. A reference pose pair, which together would enable users to control an avatar in real time. Based on the results of the observation study, the algorithm aims to find a mapping that optimizes control, intuition, and comfort. The algorithm takes hand anatomy and biomechanics as prior knowledge, which specifies the hierarchy of the hand joints and the range of motion of each joint. It takes as input avatar parameters, including the avatar's possible poses, its structural hierarchy, and the range of motion of the joints. The algorithm also takes in several interaction requirements, which can be flexibly specified by the application designers based on the use cases. These include whether unimanual control is used, the relative positions of the 2 hands, and the avatar control joints that need to be controlled. A series of constraints obtained from the observation study are also considered in the algorithm. The 1-to-1 joint mapping constraint dictates that each avatar control joint has to be mapped to one and only one hand joint. The hierarchy constraint keeps the two joint sets in a constant hierarchical order to keep the control ergonomically intuitive. The balance constraint ensures that the number of map joints on both hands are balanced if bimanual control is used. The algorithm then finds a mapping that maximizes the objective function Q, which optimizes comfortness of the gestures, hand poses structural similarity with avatar poses, and control precision. The weights for the metrics were empirically determined by considering the balance between the metrics and fine-tuned through trials. Designers can also flexibly adjust the weights for different sub-objectives accordingly to generate mappings that suit their specific purposes better. To find the optimal mapping that maximizes the objective function, ideally we should iterate over all possible combinations of joint-to-joint mappings and reference pose pairs. Yet, it's computationally extremely difficult to exhaust all the combinations. We thus reduced the search space by first optimizing the joint-to-joint mapping with a set of possible animation pose pairs with combinatorial optimization. In this step, we obtain the joint parents that maximize the objective function with estimated pose pairs. Here we get a reasonable estimate of possible hand poses G by sampling within each joint's range of motion. Possible avatar poses P include poses sampled from the avatar animations. Then with the given mapping, we find the optimal reference pose pair from the sampled animation pose pairs that maximize the objective function. We verify the effectiveness of the algorithm by comparing HandAvatar-generated, user-designed, and user-voted mappings. The 3D plot shows that HandAvatar-generated mappings have higher control, comfort, and similarity scores. To demonstrate the algorithm extendability, we generated and implemented hand-to-avatar mappings for 12 non-humanoid avatars. We evaluated HandAvatar by comparing to a baseline body-based avatar control method Kinetry. Control precision is evaluated with static posing and animation mimicking tasks. 4 avatars, including 2 observed and 2 new avatars, are tested. User experience is evaluated with a creative animation composition task on 2 new avatars. We calculated the angular deviation from this target static pose for animations as a metric for evaluating control precision. The result shows that HandAvatar allows significantly more accurate control on 3 out of 4 tested avatars. The subjective metrics from the user experience evaluation indicates that HandAvatar allows significantly better control, brings higher comfort, less physical load, and produces more satisfying animations. HandAvatar also brings comparable sense of embodiment compared to body avatar. We implemented 3 applications to showcase HandAvatar's capabilities and its potential to unlock new interaction experiences. HandAvatar contributes to the less explored non-humanoid avatar-based virtual social interactions in which users can socialize as non-humans, for example as crabs and elephants. We envision that representing users as non-humanoid avatars brings diversity to virtual social interactions, as users can carry out different activities with changing non-humanoid avatar identities. HandAvatar also allows simple, quick, and embodied 3D animation composition. We extended our implementation of HandAvatar such that the frequency of the hand movement controls the local motion speed, and predefined hand gestures can trigger frequently used avatar motions. In this example, the shark swimming speed and direction is controlled by the hand's waving frequency and the wrist orientation. 2 symbolic hand gestures can be used to trigger biting and spinning animations. Users can manipulate non-humanoid avatars and adjust their performance in real time. As HandAvatar frees up other body parts, we envision extending hand-to-avatar to body-to-thing control, which body parts can be used to provide environmental haptic feedback to the hands. We developed an application in which users' legs are used to simulate hanging cables to provide active feedback to a toucan controlled through HandAvatar. The leg's up-down movement simulates a cable's oscillation. We believe that the precise and intuitive control enabled by HandAvatar allows users to embody topologically diverse avatars in different applications. We envision this would help unlock new human as non-humanoid interaction experiences.